Hi, David from Electric Teaching here, and we're going to go with part 2 of determining the area between functions or between curves. Last one we just figured out was the purple area between the parabola and the horizontal line. That was in part 1. And now I'd like to explore what it looks like to be bounded by a cubic and a linear. In this case, a parent function of x cubed, or the mama function as I like to call it. So the mama function x cubed, and what makes 0 is the way you identify the horizontal shift. So what makes 0 here with the x is 1. So that we're going to shift the mama x cubed function 1 to the right. It means we're going to slide the saddle point 1 to the right, and then it should explode up for an initial slope of up 1 and over, and down 1 and left 1 for the other part of the slope, the other odd symmetry to this one. And then we have the line x minus 1, so regular line down 1, regular sloping line down 1. And I'm going to try to draw this in very carefully, but you're going to see we're going to get a tiny area. I want to redraw the x cubed just a little bit wider down here. So you can see the tiny little area that's exposed is right here. And a symmetrical, and that's important to recognize, a symmetrical area bounded over there on the left. Now with this symmetry, I need to remember that I could do this from just 0 to 1. Those are the two common y coordinates and common x coordinates. So if I double check at x equals 0, I get -1 cubed, which is -1. And x equals 0 up here, I also get a y value of -1. So they do intersect right here. And similar at value of 2, and similarly at the value of 2, you're going to get an intersection of +1. So we do see a symmetry here. It means I could actually run it just this little tiny first part and just double that answer to get the total area in orange. Or I could run this in two different integrals, but I have to remember top function minus bottom function. So I'd like to do it both ways just to show you that they will be equal, and just to emphasize the top minus the bottom in case you don't have symmetry and to really understand how that works. So let's take a look. If I look at the first integration, it is from 0 to the x value of 1, 0 to the x value of 1, and the function on top is the cubic. The function on top is the cubic. So that would be the x minus 1 cubic on top. Okay, and then below it would be the linear x minus 1. So we're going to subtract off the x minus 1 dx. Then I would have to add technically another function, another integration. The second part of this would be adding the integration of not 0, but from 1 to 2, where we have a flip-flop of what's on top and what's on the bottom. If you remember here, I had to redraw this so that the bottom was clearly the cubic underneath here. Okay, and the top was the line. And so in this case, in the second problem here, we would have then on top the x minus 1, and on the bottom the cubic x minus 1 cubed. X minus 1 cubed. Again, this would be dx to get the full integration symbol across. Now, let's go ahead and try to integrate these and get them separately, and then see what happens if we were to double them and take a look, and do they really do match. All right. You can see I always have my students approximate the area so we don't get any ridiculous answers. We're looking at less than half of a square unit, less than half of a square unit. I mean, it clearly is less than half. So let's anticipate that answer to be less than half and see where it's at. To integrate this one, I could use U substitution to really accelerate the process, to let U equal x minus 1 on the inside here, and that du would be, derivative here would be 1, dx. So du is actually equal to dx. So when the derivative of the inside is 1, or when you use substitution and du is equal to dx, you simply have a u cubed here. So as I like to tell the students, a shortcut is when the derivative of the inside is 1. Just go ahead and take the derivative of the outside and you're done. So the derivative of the I keep saying derivative. I apologize. Integration, when the derivative of the inside is 1. Go ahead and take the integration of the outside as if there was just a u on the inside. So integration of outside is x minus 1 to the 4th, add 1 to the exponent, flip, and multiply. Integration over here, let's go ahead and just do this in a very careful, methodical way. Scratch work here, minus x plus 1. So the integration here is a minus, okay, 1 half x squared, and then plus an x. And we're going to be running this on 0 to 1, So a quick way to do this integration is to identify that the inside of this, so you don't have to expand the cubic here, the inside of this derivative was 1. So shortcut, just integrate the outside and you are done. Because du equals dx, this works. And then simple integration over here. Okay, finish it off at 1. At 1, this whole thing is 0. At 1, this is minus 1 half. At 1, at x equal 1, this is plus 1. At 0, over here, you got to be careful. At 0, we're going to be left with a 1/4 and a negative 1 to the 4th. At 0, so we're going to subtract off the plug and chug of 0. And we're going to get 1/4 times a negative 1 to the 4th. So we're going to get minus 1/4 there, minus 1/4 there. So our total answer here is 1 minus a half to leave a half. So these two are a half, and then a half minus a 4th is equal to 1/4. We expected the answer to be less than 1/2, and it is less than 1/2, so this seems to be estimate-wise correct. Let's look at the integration for the other one over here. Kind of do this in a speedier manner. In fact, let me just pull this over here so I can do that problem right here underneath. All right. Now, with this problem, let's go ahead and integrate again x, the integration of x, 1/2 x squared, minus 1 will be minus x. The integration of this, as we've determined over here, will be minus the 1/4 x minus 1 to the 4th. We are running this from 1 to 2. This answer, this calculation will be from plug and chug at 2. So this will be equal to 1/2 times plug and chug at 2, a 4. I always like to write that 4 a little bit higher so I can see the quick cancellation. Okay, minus the plug and chug of 2 is 2, minus the plug and chug of a 2 here will be 1 to the 4th, so the only thing left will be minus a 4th. At 1, we are going to be then subtracting at 1 a half. We are going to be plugging in a 1 here, and we're going to be subtracting. This is important. In fact, I'm going to group this with a subtraction symbol just to be safe. Most of my students, almost like I did there, start to get a little hasty on what I'm doing with the second plug and chug, where I'm supposed to be putting in and evaluating, substituting, evaluating x equal 1, and subtracting off the total calculation. Some students, including myself, get a little hasty here. So let's be really careful. Let's subtract off the whole quantity. So minus the plug and chug of a 1, half, good, minus 1, so now I'm just going to be able to safely plug and chug without worrying about any extra minus part. and then minus the plug and chug of a 1. Well, plugging in a 1 here is 0, so this will be 0. So we're actually at the end of our calculation. At the end of our calculation. Quick little work here. The 4 and the 2 cancel and leave a 2. The 2 minus 2 cancel completely and leave nothing. So now what do I have left? I have a minus quarter and a minus, what's inside here? A minus quarter and a minus a negative half. So a minus minus half leaves a positive half with the minus quarter, and we do get a total value of 1/2 minus a quarter, again of 1/4. And we were estimating the second one to be a 1/4 as well because of the symmetry. We were correct. We could have just done the front end and doubled it. Final answer, 1/4 plus 1/4 equals 1/2. I always find that very intriguing, that the area bounded by this really neat looking cubic curve here, okay, which has a varying heights all the way through, will end up being a perfect little rational of 1/2. I always find that interesting. So if we take a look at a graphing utility, and I've built one with Python, I've coded one out with Python, and I've actually have a video sequence on how to build one of your own. I think this is a really nifty teaching tool as well if you're into programming and making your own little personal grapher. It's a great one to use, so you can find this on my YouTube channel. And what we're going to do is take a look at that integration and via the calculator or a graphing utility. So it was x minus 1 cubed. So let's graph that one. You can see there's the cubic. I'm going to add another graph here, and it was x minus 1. And then if I say to integrate in my little program that I've made here between the values of 0 and 2, it'll show that the trapezoid approximation is 0.4992, as well as the left end and right end because of the symmetry, and that always happens. So what we've taken a look is, using trapezoid approximation, we've taken a look at how, approximately what it is, which matches our exact value that algebra was able to determine. So we have taken a look at how to do this by hand and get the exact answer, how a calculator may get an approximation of it, and so that way you have a really good idea of what it is to get the area between the curves. This concludes this little sequence of part 1 and part 2 of area bounded by curves. I'm David from Electric Teaching, and I hope that I have helped.